Hi, I'm Dr. Carl Otico, and I will be your guest lecturer this week. What? Never had a space manatee as a teacher before? I assure you that I'm adequately educated. Now, let's talk about integrated rate laws. Rate laws are an expression of how fast a reaction is proceeding by using the concentrations of reactants as a measuring tool. Rate laws depend only on the concentrations of reactants and the reactant's rate constant, or K. Rate laws tells us the rate of the reaction given the concentrations and time intervals. This is a valuable method. However, what if we have a chemical reaction and we want to know what the concentration of reactant will be at a specific time after the reaction started? For example, let's consider our old friend, the decomposition of hydrogen peroxide into water and oxygen gas. The rate law for this reaction looks like this, and we could use experimental data to determine the value of K for this rate law. We could then look at the concentrations of hydrogen peroxide and know the rate. However, if I asked how much hydrogen peroxide is left after 5 hours, this rate law doesn't help us very much. However, we have seen how these rate laws are related to the slope of the concentration curve versus time. Slopes are derivatives. Thus, these rate laws are derivatives of the concentration versus time graph. Integration is the process of undoing a derivative to get back to the original equation. Thus, if we integrate the rate law with respect to time, we will get the equation of the original graph. This graph. This will allow us to plug in a time point and get a reactant concentration at that time. Pretty neat. To save time and money, I will do the integration for you. You will not be responsible for repeating this integration. However, you will need to know how to work with the resulting equations. First, integration of a first-order reaction. Here is a generic first-order rate law. We have seen that this rate law is basically equal to the negative slope, or the negative change in concentration divided by the change in time. Do you remember why it is negative for reactants? We can rearrange this. Integrate between time equals 0 and some arbitrary time t. The integral of a derivative of something over itself is the natural log of that thing, in this case, concentration. For the other side, the integral of a constant is just that constant times the variable. Time 0 becomes 0, and time t is k times t. We can rearrange this a bit, and we get the natural log of the reaction constant is equal to negative kt plus the reactant concentration at time 0. What does this equation look like if you blur your eyes a little bit? Yup, it's a linear equation in the form of y equals mx plus b. For this graph, y equals the natural log of the concentration, and x equals time. So we can use this equation and graph to determine the concentration of reactants at any point during the reaction. We can do the same process for both second-order rate laws and zero-order rate laws. For second-order rate laws, we get this integrated equation. Again, this is a linear graph of 1 over the concentration versus time. Zero-order reactions, where the rate is equal to the constant K, integrate to this linear relationship, where a graph is just the concentration of reactant versus time. I proudly present to you zero, first, and second-order integrated rate laws. Consider the graph of these rate laws. What are the units of K for each of them? Remember that K takes the units which cause the equation to work out correctly. Thus, the units for K for a first-order reaction would be 1 over time. For a second-order reaction, they would be 1 over molar times time. And for a zero-order reaction, these graphs can be helpful in identifying the order of a reaction, even when you only have K for that reaction. Let's see what we can do with these integrated rate laws. The reaction A goes to 2B plus C is known to be a zero-order reaction in A, and to have a rate constant of 5 times 10 to the minus 2 molar per second at 25 degrees Celsius. An experiment was run at this temperature, where the initial concentration of A was 3 times 10 to the minus 3 molar. We know that this reaction is a zero-order reaction in A. Thus, we can use the zero-order equation. So, the concentration of A at any time is equal to negative K times T plus the initial concentration of A. We have the initial concentration, and we have K, which gives us this equation. We can simply plug in for time t and solve for the concentration of A. We get 2.8 times 10 to the minus third molar. If we started with only A, what is the concentration of B after the same time? We need to subtract the initial concentration from the final concentration of A. We can then do a simple molar ratio since we know that 2 moles of B are created for every 1 mole of A used up. We simply multiply by 2 and get the concentration of B as 4 times 10 to the minus 4th molar. Scientists often use the term half-life when referring to radioactive decay, but we can also think about how long it would take the concentration of a reactant to reach half of the starting concentration. For a first-order reaction, we can manipulate the equation to get a simplified half-life equation. You should be able to work out this calculation on your own. Let's solve for T since that is what we are interested in. Substitute the value of T as T1 half. The definition of half-life is when the concentration of reactant has been cut in half. So we can say that T1 half, the concentration of A at that time, equals 1 half the initial concentration. We can drop that into our integrated rate law, simplify, and get T1 half equals 0.693 divided by K. Go ahead and calculate the integrated rate law for the half-life of 0 and second-order reactions now before you continue. You should have equations that look like these. Consider what the units of K are for each half-life reaction. We can often identify the order of a half-life reaction by the units of K. It is important to note that while seconds and molarity are common units, we could have concentration and time in other units, but that wouldn't affect the reaction order. We will see that in our example. Let's give it a try. A certain synthesis reaction has a rate constant of 0.761 per minute and a starting concentration of reactant of 0.540 molar. What is the half-life of this reaction? First, what is the reaction order? From the units of K, we can see that it is a first-order reaction. Great. Now we can use the half-life equation for first-order reactions and solve for time 1/2. We get 0.911 minutes. Read and work through pages 66 through 69 in your workbook. Studies of chemical kinetics ultimately deal with 3 specific questions. 1. How fast does a reaction take place? 2. How can we change the rate of a reaction? And 3. How does the reaction take place? We looked at number 1 when we considered rate laws for chemical reactions. We covered number 2 when we looked at the integrated rate laws and how to affect rates through changes of concentration of reactants. However, now we need to take a closer look at the mechanisms of reaction and how they affect the reaction rates. Collision theory of chemical reactions. Collision theory is based on 3 postulates. 1. The rate of chemical reactions is proportional to the rate of collisions of reactant molecules. The collisions must be oriented such that the atoms which collide are the ones that will form a bond. And 3. Collisions will occur with sufficient energy to overcome the valence electron repulsions and allow for redistribution into bonds. These are somewhat intuitive. Take carbon monoxide, for example. If we react carbon monoxide with oxygen gas, we get carbon dioxide and elemental oxygen, according to this chemical equation. For one of the gaseous oxygen molecules to bond with the carbon dioxide, they must make contact in the correct orientation. Consider these 2 collisions. Which one will most likely create the needed bonds? It is this one, where the oxygen and the carbon collide. They also must have enough energy to allow for penetration of valence electrons and rearrangement. When a correctly oriented collision takes place and the molecules have sufficient energy, they will form a hybrid state. This is referred to as an activated complex, or more commonly, the transition state. This transition state only lasts for a brief instant. These types of collisions seem like they would be pretty rare, but the higher the concentration of reactants, the more likely they are. Thus, the rates increase with increased reaction concentrations, as we have seen. The energy of these collisions is a major hurdle for many reactions to get over. We can visualize the energy of collisions during chemical reactions by looking at a generic example. For the reaction A plus B goes to C plus D, we can draw an energy curve for the collisions between A and B. We can see that during the collisions, the total energy of the collision must reach high enough to form a transition state. A and B start out with a specific energy. If they collide with enough energy, they form a transition state and then resolve to the new product C and D. Is this diagram endothermic or exothermic? The energy difference between A and B and the transition state is called the activation energy. The difference in energy between the reactants and the products is the enthalpy change. So, for this reaction, it is endothermic because the final energy state is lower than the initial energy state, and the reaction will give off heat. However, in this diagram, the products occupy a higher energy state than the reactants. This reaction is endothermic and takes up heat from the surroundings. Both the likelihood of proper collision and the energy needed at any particular temperature can be expressed mathematically as the Arrhenius equation. If we do some manipulation, we get a more usable form. Notice that this is also linear in the form of y equals mx plus b, where the negative activation energy divided by the gas constant is the slope, and y is the natural log of k. A is the frequency factor that considers how likely correctly oriented collisions are. Another way to write this equation is like this. This allows us to relate the reaction constants and temperatures between two different conditions when we have the activation energy of a reaction. It's important to note that if the activation energy decreases, the rate constant increases and the reaction will be faster. This also means that an increase in activation energy will slow the reaction down. Think about collision theory. If the molecules must collide with a higher energy, then they are going to do so less often. Let's use this last form for an example. A reaction has a rate constant of 0.0482 per molar second at 64 degrees Celsius and has an activation energy of 24.9 kilojoules per mole. If the temperature increased to 120 Celsius, what would the rate constant become? So, K1 is 0.0482 per molar second. Temperature 1 is 64 degrees Celsius, and the activation energy is 24.9 kilojoules per mole. If the temperature increased from 64 to 120 degrees Celsius, what would the rate constant become? We need to convert our temperatures to Kelvin so that we can use the gas constant value of 8.314 joules per mole Kelvin. Now, we plug our numbers into the equation, and solving for K2 gives us 0.171 per molar second. Read and work through pages 70 through 74 in your workbook. Also, make sure that you read chapter 12.6 in your textbook and work through the pages 75 through 79 in your workbook. Next week, Dr. Copley-Salem will be back to talk about equilibriums, one of his favorite topics in all of chemistry. Peace.